Hey, little puppers. What do you see? What's going on? Nope, not that. That's not for you. What's up? Hey, puppers. Yep. Alrighty. Let's put that into place. That was Peebs, the puppy. And we have a problem for AP Physics 1. So, hey, it's Mr. K. Screwed up today a little bit. Did a problem. Surprised nobody caught it. But that's alright. We had a... What are you doing, Peeps? We had a Pulley Atwood machine. And where did my ruler go? Looking for my ruler. Don't know where it was. Doesn't really matter. Alright. Well, an Atwood machine is one where you have a mass on the left side and you have a mass on the right side. And that is a big freaking pulley. And so usually these masses are going to be different. One definitely heavier than the other. Going to work this with variables though. So that's M1, M2. This is going to be M3. It's going to have a radius R. And we're going to talk about the inertia of this. This is going to be a disk, so we're going to have a 1/2 in front of it. M3 in this case, R squared. So let's talk. We have a pulley. I'm going to solve this two ways. There was another video that I did where we solved it two ways. But specifically, this is the one from class, and I admittedly did not put in a conservation of energy term that I just forgot about because I guess I was rushing. But you know, even I make mistakes. So I'm going to go back, look at this again. So let's talk about how this will move. Now, if the masses are the same here and here, it's not going to accelerate. So we're going to assume that M1 is going to be, let's make that bigger. M1 is going to be greater than M2. And so if that's the case, then this whole system will, like that, assuming that there's not enough frictional torque to keep it still. You know, torque can, or friction can cause torque. If you ever had like a pair of rollerblades or, you know, skateboard or it's any kind of wheel, that wheel about the axle will slow down eventually. And that's due to frictional torque right here on the axle and where that wheel sits on it. So we're going to neglect that. We're going to say that's 0. If we do, then we're going to have to talk about what forces are causing the motion. So here M1 has a force downwards, which is going to be M1G. M2 is also going to have that same kind of force downwards, so it's going to be M2G. Shouldn't have drawn these the same length because we know that M1G is going to be bigger than M2G, but oh well. There will be a force of tension upwards, and the question would be, you know, which way do these move? And these will move in a counterclockwise fashion because M1 is bigger than M2. And so we're going to assume that if that's the case, tension on the left side will not be, call it T1, as big as M1G. Can't, because if this is going to accelerate down, tension needs to be less. However, if this is going to accelerate up, the tension on the right side will have to be bigger, call it T2, than M2G. So respectively with each other here, T2 would be bigger than M2G, T1 will be less than M1G, so that we have the accelerations doing this. And then a little bit of misconception that I ran into today was that how does tension work? Well, tension on this mass is definitely pulling it up. Tension on this mass is definitely pulling it up, but if you look at how that tension is attached to the pulley, it's going to be trying to pull down here with T2, and it's going to be trying to pull down there with T1. Okay, and so if that's the case, if this pulley is going to rotate counterclockwise, then T1 will be bigger than T2. And so just consider if you have, if you have a, let's say the ceiling, you got a string hanging down from the ceiling and you've got some mass hanging off of it. If we were to consider the mass that's hanging down, we know that the string's pulling up on it. But then again, if you go to the other side, the string is pulling down on the ceiling. It's the same tension, just different ways. You know, if you were to walk over and actually grab on and pull that mass up, then the string would be pulling your hand down while you were trying to pull the mass up by applying tension the other way. So here we just do sum of all forces. I'm going to call counterclockwise to be my positive, clockwise to be my negative. And so if I look at M1, I'm going to have M1G trying to move it, and then tension 1 is going to be fighting it, and that equals M1A. Go to the other side, same kind of deal. We've got T2 trying to move this thing upwards, so I'm going to call that positive. T2 minus M2G, sum of all forces on the object equals M2A. So force minus force equals force, net force is equal to ma. So that's what we got here. Solving this for tension, I'm just going to do this right now because I know I'm going to use it later. Tension 2 is going to be equal to m2a plus m2g. Other side, do a little switcheroo. m1g minus m1a is equal to our tension 1 on the left side. So we've got these two equations of tension. We're going to use those up here whenever we talk about torque, because not only do we need to consider a sum of all forces, but also a sum of all torque. So sum of all forces on individual items, there would be a sum of all forces here, except that we're going to call that to be a net force of 0, because this thing isn't going to translate up and down, left or right. The pulley's the pin in the pivot point is going to take care of that. By the way, if you need to pause this video, pause it. Go back, because we are talking about the same stuff, but it's also new stuff in a sense that we're talking about rotation. So on to torque. This pulley will rotate in a counterclockwise fashion because there are two forces trying to apply torque to it, but this one wins. T1's going to win. T2 should lose if this thing is going to rotate the way that we want it to. So I'm going to go up here and I'm going to say, all right, the sum of all torque on our pulley is going to be equal to our T1. Notice how the T's are a little bit different. And that's going to be at a radius r. Remember how torque is a force. It's like the rotational analog of force, but it's going to be a force at some distance. And if you notice, it's perpendicular to this radial distance to the axis. Okay, sometimes you're going to have to take an angle and use sine or cosine to find the component that is perpendicular. Here it's already perpendicular, so we're good. Minus T2 is fighting it the other way, so T2 at radius r. It's the other side. Those two torques, there's going to be leftover torque. Leftover torque. Torque is a force at some radius perpendicular, but remember it is also equal to some I alpha if it's unbalanced. So these two torques, hey, it's unbalanced, it's going to be equal to I alpha. And we'll do you one better. We know the inertia of the system is going to be 1/2 m3r squared, and then we multiply by alpha. Okay. Looking at this is going to get a little mathy. That's okay if you get lost in it. Again, you can pause it whenever you want. At the end, it's going to be very clear as to what happened. So I'm going to divide everything by r. If I do that, that r goes away, that r goes away. Of course, I'm going to divide this by r just to be mathematically appropriate, but really don't need that anymore. Dividing this right side by r gets rid of one of these r's. There are two there. And so it gives me tension 1 minus tension 2 should be equal to 1/2 m3r alpha. And then the last thing that we're going to do with this before we start plugging more stuff in is to realize that angular acceleration, that's the amount of angles that this thing goes through and accelerates at per second every second. If we multiply that by r, what we get is the tangential acceleration of the edge. So this edge here, it starts off at rest, and it's going to speed up as the system starts to rotate and accelerate. Well, the edge will accelerate at a certain rate. The middle will accelerate at a certain rate. It's all accelerating at the same angular velocity, but tangential acceleration is what I meant to say. The same tangential acceleration. That's actually going to be different based on how far out you are. Okay, that should make a little bit of sense. So if you were to swing your arm in a big circle, the thing that's going to be moving the fastest by the end of that turn, if you were to do it fast, it would be your hand. Okay, and that means it would have a larger acceleration tangentially, and that tangential acceleration would happen to also be the acceleration of this guy going down, the acceleration of this guy going up. All right, so alpha times r, that's going to lead us back to the tangential acceleration of the edge, and so I can just say, hey, that's going to be 1/2 m3 a, and that a is the exact same a that we're talking about down here. Okay, and now since I already solved for them earlier, I'm going to plug in T2 over here. I'm going to plug in T1 right here. So use parentheses just to make it a little bit easier to look at. T1 is m1g minus m1a. T2, got that, is going to be m2a plus m2g in parentheses equals 1/2 m3a. Okay, and then we can go ahead and take these parentheses off, because that's not a big deal, but these parentheses are kind of necessary unless we distribute this negative in. So negative and negative, and so what we get here is m1g minus m1a minus m2a minus m2g equals 1/2 m3a. And again, this is math. It's very algebra heavy at the moment, but let's make it look a lot nicer. let's move all of our A things to the right side. And if you notice, that's negative MA, that's negative MA. It's going to move it to the right side. That's going to leave behind M1G and M2G. M1A goes to the right side, and M2A goes to the right side. These become positive, because we're adding them to both sides, plus 1/2 M3A. Okay, and then again, every single thing has A, so we can factor out an A by dividing everything in here by A. That'll just go away, that'll go away, that'll go away. And then the last step would be to divide all this mass, M1 plus M2 plus 1/2 M3, to the other side. And yeah, you can say I can factor out the G, but I really don't want to. It looks so much nicer if I don't. Just to me. M1 plus M2 plus 1/2 M3, and that equals A. So what we have here is something that's very elegant, actually. Think about what this is. M1G, that's this force going down. That's minus M2G, that's this force going down. Those are the outside forces on the system. And there's going to be a leftover force. So M1G minus M2G is still force, right? And force is equal to MA. Hey, if we divide force by mass, we get A. What do we divide these by? Well, we just divided by all the mass. And then the last part has 1/2 in front of it because the inertia term has that 1/2 in front of it. So by doing this, actually by understanding this, we could have skipped everything and just said, hey, what are the outside forces? Well, that, and they're fighting. What is it trying to move? Well, this guy, M1, this guy, M2, and M3, but let's put the 1/2 in front of it because there's that inertia term, because it matters where the mass is placed if you rotate something. So, and then if you divide out, that should equal A. If you know A, then you can find out things like final velocity. You know, if you knew how far it fell, let's say there's some kind of delta H, or you can find out final velocity, you can find out the time, because that just becomes kinematics. And so the second way to do this is we're going to use energy. So looking at energy, you know, this is all forces and torque. This is like the basic way to do it, kinematics. Energy would be a little bit faster, but you got to make sure you keep all the terms in there. And remember, I forgot to put in one of the terms in class. So let's make sure that I don't forget now. When M1 and M2 start off, they're at rest. And M1 is going to fall down. M2 is going to rise. So M1 able to fall down a certain distance, we call it H maybe. M2 is going to rise a certain distance, also H. So essentially, what we need to talk about is how far delta H M1 fell and how far delta H M2 rose, which is the same H. But we treat the energy a little bit differently. One is losing potential energy, the other one's actually gaining it. So for our energy term, initial energy is equal to final energy. The initial energy here is all just potential energy. Put the Earth as part of the system. M1G is going to be our force, and then H, this delta H, the change in position. I don't care what the actual positions are, I just care about the change in heights. That will be the initial energy that we have. So let's say M1 goes down. At the same time, M2 is going up, so it's going to be gaining some M2G delta H. Okay? So again, while one goes down, loses potential energy, the other one's going to go up and gain potential energy. So at the end, the other thing that's happening is not only has this raised up, but also things are moving. M1 is moving, so 1/2 M1V squared. M2 is moving, plus 1/2 M2V squared. And that's spinning, so plus 1/2 I, which is 1/2 M3R squared, omega squared. So translational kinetic energy, 1/2 mv squared. Rotational kinetic energy, 1/2 I omega squared. The M turns to I because now you got to care about where it's placed. The V turns to omega because now it's just angular velocity, radians per second. Looking at this, no, I can't divide by all the mass because not all the mass is the exact same. It would be really nice if it was, but it's not. Plus, I don't want to mislead you. But what I could do here is I can just move the M1GH and M2GH to the same side because it's just this difference in potential energy that's occurring. M1G delta H minus M2G delta H. And then the other thing I'm going to do is I'm going to multiply everything by 2. So I'm just going to put a 2 out here. And what that should do is that should take off these halves, halves, halves. and leave behind their mv squareds. So that's going to be m1 v squared plus m2 v squared plus the half is still there for the 1/2 on the inside. That didn't cancel out. M3 R omega is going to be just like how we kind of did up here. R alpha was A. R omega is just going to be V. It's going to be V squared. And so now what we can do is we can say, all right, can we do anything with this? And the answer is yeah. This is V squared, that's V squared, that's V squared. It's the same thing that happened before. And we can just say, all right, M1 plus M2 plus 1/2 M3, all that, we factor out the V squared. The left side, we still got the same stuff. Tell you what, H is the same, G is the same, so let's go ahead and do this. 2G delta H M1 minus M2, and then we're going to have to divide. So my last step would be to say, hey, let's divide out all those M's. 2G delta H M1 minus M2, divide all that by M1 plus M2 plus 1/2 M3, and that will be equal to V squared. I'm just going to square root there. So not as pretty as I would like it, but this is sort of the same solution as your square root of 2gh. In fact, it's there. So let's do this real quick. Let's run through some numbers. I know this video is getting a little bit long, but let's go ahead and run through some numbers. Let's make M1 10 kilograms. Let's make M2 5 kilograms. Let's make M3 another 10 kilograms just for the heck of it. Let's just make R1. Okay, 1 meter. And then H, let's make that delta H 5 meters. And so if that's the case, I can go over here and say, all right, plugging numbers in, M1 is 10 kilograms, so that's 10. G is 10 minus M2 was 5. G is 10. All right, divide that out. M1, 10. M2, 5. Half of M3, 5, because M3 is 10. So what is this? 10 times 10, that's 150. So I have 50 on top. 50 divided by 20. What's 50 divided by 20? 25. 50 divided by 20, stupid me, yeah, 25, 2.5. So that's 2.5 meters per second squared. This is also getting late for me. If I know that, if I want to find out my final velocity, I know that this is my acceleration. Final velocity squared is equal to initial velocity squared, 0, plus 2 acceleration, change in height, 5. All right, what is that? 2.5 times 2. Oh, well, yeah, okay. Square root of 25 is 5. So final velocity is equal to 5 meters per second. This one's going down 5 meters per second. This one's going up 5 meters per second. Let's make sure that this checks out over here. And so I'm going to say, all right, if this does check out, hopefully 2 right there, G is 10, H, delta H is going to be 5. The M1 minus M2, 10 minus 5. Divide all that by M1 plus M2 plus half M3. What was that, 20 over here? All right, and we're going to square root that. Let's make sure this all works out. 2 times 10 times 5 times 10 minus 5 times 5 divided by 20. That's fantastic. Square rooted, just for the heck of it, gives me 5. So we definitely worked the math out correctly. Energy one way, torque and kinematics and forces the other way. We get the same final velocity for these masses, and the edge velocity is also 5 meters per second. So you can work it whichever way you want based on your initial conditions. This, again, this is not with any kind of frictional torque. If there was frictional torque, the accelerations would be a little bit less. But there you go. That's the solution. 19 minutes, 31 seconds. Ended.